Welcome to the Explainer. Today, we're diving straight into the absolute cutting edge of artificial intelligence. And we're going to kick things off with a very simple yet incredibly frustrating question. Why is it that an AI can write a flawless Python script in 2 seconds flat, but it can't figure out how to fold a t-shirt? It's a real head scratcher, right? Well, this is known as the Moravec paradox. It highlights this fascinating reality. We have completely mastered language with brilliant systems like ChatGPT, but artificial intelligence still deeply struggles to understand the physical world and basic physics. It can't navigate a messy kitchen. And why? Well, because the purely digital realm of language is vastly different from the chaotic, friction-filled reality of the actual physical world. So here's our flight plan for today's Explainer. We're looking at the physical AI problem, going inside large language models, figuring out what world models actually are, doing a heavyweight showdown between LLMs and world models, exploring the hybrid AI future, and finally unlocking autonomous agents. Let's get right into it. Section 2. Inside Large Language Models. The Brilliant but Blind Librarian. Okay, so think of an LLM as a highly erudite librarian. This librarian has memorized every single book, map, and driver's manual ever published. If you ask them to describe driving a car, they'll give you a perfectly fluent, step-by-step description, but here's the catch. They've never actually experienced gravity. They've never felt the friction of wet tarmac. The mechanism driving this brilliant but physically blind librarian is autoregressive next token prediction. Regardless of the exact architecture under the hood, it essentially acts as a giant conditional probability mass function. It takes your prompt, looks at its vast internal states, and just mathematically predicts the statistical likelihood of the very next word. Now, while they are absolutely phenomenal at generating text, retrieving knowledge, and writing code, they have zero persistent internal physics engine because they're just predicting statistical text correlations rather than actually simulating physical reality. They constantly hallucinate physics. They don't intuitively understand that a glass pushed off a table will shatter because they don't have a causal understanding of time, spatial dynamics, or material properties. They literally just know that the word shatter often follows the word fall. Which brings us to Section 3. What are world models? The internal flight simulator. This represents a monumental shift being led by pioneers at Meta and DeepMind. Instead of a well-read librarian, I want you to think of a pilot sitting inside a high-tech flight simulator. A world model is exactly that, an internal simulator of reality that learns transition functions. That's really just a mathematical way of answering the question, if I am in this current state right now and I take this specific action, what exactly happens next? It predicts the physical consequences of an action before it ever executes it in reality. This concept is so absolutely fundamental to the future of AI that Yann LeCun, one of the founding fathers of deep learning, recently raised $1.03 billion for AMI Labs. And the sole explicit purpose of that funding? Training world models. Not language models, not image generators, world models. He firmly believes that true intelligence requires these predictive models of the physical world rather than just pure pattern matching on text. So how does a world model actually learn? It happens in 4 brilliant steps. First up is observation, where it encodes reality. Second, it imagines possible futures. It is literally rolling forward different action paths in its internal dreams. Third, it plans by evaluating which of those imagined trajectories gives the best reward or avoids disaster. And finally, step 4, it acts. By doing all this mental rehearsal first, it drastically cuts down the need for slow, dangerous trial and error out in the real world. But look, predicting the future is hard. It's especially hard if you're trying to generate every single pixel of a video frame. That just wastes massive computing power on irrelevant visual noise, like trying to predict the exact shadow of a rustling leaf. That's why architectures like LeCun's JPA, or Joint Embedding Predictive Architecture, are a total game changer. They don't predict exact video pixels. Instead, they predict the abstract, latent essence of how things change. They're predicting the idea of a ball rolling, completely tossing out the visual noise that just doesn't matter for decision-making. Section 4. LLMs versus world models, the heavyweight showdown. The core difference really comes down to this. Large language models rely on mapping inputs to outputs based on language statistics. Now sure, some do develop implicit spatial maps, like the famous Othello GPT that figured out the shape of an Othello board literally just by reading game transcripts, but they still completely lack the explicit, closed-loop feedback you need to learn actual physical causality and do safe counterfactual planning. World models, on the flip side, rely entirely on physical intuition and causal grounding. When you place their applications side by side, the split is crystal clear. LLMs absolutely dominate the digital and conversational space. Chatbots, email productivity, coding, you name it. But world models? They are poised to completely take over everything physical. We're talking robotics. We're talking autonomous self-driving cars that generate their own edge case weather simulators, like Waymo does. And we're talking about rendering photorealistic interactive video games completely on the fly. World models bring some incredible advantages to these physical domains. The biggest one by far is unmatched sample efficiency. Take an algorithm like Dreamer v3. It has this unprecedented ability to master over 150 diverse tasks, including the insanely complex Minecraft Diamond Challenge, entirely from scratch. And how does it pull that off? Because it trains its policies inside its own hallucinated simulation. It achieves massive efficiency without needing millions of physical, real-world interactions. It gives machines the actual power of safe mental rehearsal. Now, to be fair, they are still a highly emerging science, and they come with some severe hurdles. World models are notoriously complex to train and stabilize. They're super vulnerable to something called representation collapse. That's basically where the model gets lazy and just maps all inputs to a single constant vector to cheat the prediction test. Plus, when they imagine the future, tiny little inaccuracies can compound exponentially over long horizons, which leads to hallucinated broken physics. Fixing this requires some really delicate mathematical regularizers, like the SIDGE regularizer recently proven in the 15 million parameter Lie world model, which forces the data into a healthy Gaussian distribution. Section 5. The hybrid AI future. World models plus LLMs. The absolutely crucial point here is that this is not a winner-take-all battle between text prediction and physics simulation. We are rapidly moving toward hybrid autonomous agents, where the brain is seamlessly divided into two complementary halves. We're looking at an architecture where 50% is dedicated to reasoning, semantic logic, and communication, and the other 50% is a dedicated physics simulation and sandbox, both halves working in perfect unison. Think of it kind of like this. The LLM will act as the high-level symbolic planner. It will understand your instructions, fetch relevant knowledge, and set the broader goals. Meanwhile, the world model acts as the local, physics-grounded simulator. It'll take those goals and safely test the physical consequences right there in its latent sandbox, making sure the physics actually work out long before a real robot ever lifts a single finger in your living room. Section 6. Unlocking autonomous agents. The path to physical intelligence. By combining the vast semantic reasoning capabilities of vision language models with the explicit physical planning capabilities of latent world models, we are finally bridging the massive gap that has held robotics and physical AI back for decades. We are actually building true, robust autonomous agents. But to really appreciate the sheer scale of this challenge, look at this number. That is 86 quadrillion. According to some research, 86 quadrillion is the estimated number of parameters needed to simulate a human brain's vast interconnectedness and physical intuition. It's a stark reminder that true physical intelligence requires a monumental leap well beyond just predicting the next word in a sequence. It requires an engine that truly, deeply understands reality. So, as we witness this cosmic shift in technology, moving from AI that just talks to AI that truly understands and navigates the physical world, we have to ask ourselves, how will physical AI transform your specific industry? And honestly, more importantly, are you ready for a world where machines can literally imagine the future before it even happens? Keep that in mind as we watch this space evolve. Thanks for tuning into this explainer and keep questioning the technology around you.